Okay. All right, spring break's almost here. I hope not too many of you had your plans canceled by the horrible virus. I'm supposed to go to Portland. We'll see how that works. But OK, so let's pick up where we left off. We were doing a priority queue. And the way we were doing it was by building a binary min tree, which is a lot like the binary search tree that you guys are doing for the assignment, except with a different set of invariants, right? So where a binary search tree, the idea is that we want to be able to find any element very quickly. And therefore, we want to essentially keep them in some sort of order, a sorted order. The binary search tree invariants basically say everything on my left, in my left child, is smaller than what's at my root, which is bigger than what's on my right. And that way, when we're trying to put something into a binary search tree, as long as we abide by those invariants, we know exactly where anything we put needs to go. And then when we're looking for something, we can find it, right? Because it's either at the root, or if what we're looking for is smaller, we look left. If we're looking for it is larger, we look right. We can find the min and the max pretty easily by just going left until we can go left no further, or going right until we can go right no further, and find the min and the max. And otherwise, the binary search tree does a nice job of keeping everything in a sorted order with average case log n log n performance, right, for getting things in and out. Now, when we're doing a priority queue, we only want the smallest thing. And we realize that, well, with the binary search tree, we're actually doing more work than we're required to do because we are keeping everything in order. And this average case behavior is only average case. There's bad worst case behavior because the shape of the tree is dictated by the relative sizes of the things that we insert and the order that we insert them in. And so using that insight, we posited that, well, we could be more efficient, or at least be more guaranteed about our efficiency, if we created what's known as a binary min tree, where the invariants are different, right? The invariants help us with a priority queue, where we're only looking for the smallest item ever. And right, we have a queuing discipline where it's lowest priority is the next one out, right? So the invariants for a binary min tree were that the thing that's at the root, the value, is the smallest of anything in either child. And that's it, right? We don't need everything in the left to be smaller than everything in the right or anything like that. We just need the thing to be at the top to be the smallest thing, period, right? And then, because what we're trying to do is to be able to efficiently add things and take things out, we want to essentially make sure our left child and our right child are balanced in height. And so we say, OK, the other invariant is that we're going to put things into our children in such a way that where they'll never be more than one off of each other in terms of their height, right? And then, of course, the recursive nature of this, that our left child and our right child are binary min trees in and of themselves. And so doing that, right, we end up with still order n log n performance for using a binary min tree as a priority queue. But we can now guarantee that it's order n log n because the shape of the trees are always even. We can't possibly get any really unbalanced trees, and so we always get nice, good n log n performance. Now, we're eventually going to go to something called a binary heap, which will do give us the exact same performance guarantees, and is easier to implement because we don't have to move. We can do it as a list, and we'll see that at the very end of today. But what we did get through in terms of the binary min tree, we were kind of coding it up in class. So we got all the way up to enqueuing. We didn't do dequeuing. We just did enqueuing. But the enqueuing that we did was pretty, already exhibited a couple of things that were interesting. The first was this idea of gluing the priority and the value together in a little kind of, by creating a little prioritized value interface and an implementation. And that happens a lot, where you have two different things that you need to kind of glue together in order to deal with internally, and then you're going to, you're going to unglue them when you need to to return the value back out to whoever's using this, this binary min tree. So we saw that, right? And so after we glue them together, right, so essentially our NQ and DQ operations for our binary min tree will take in, for NQ, a value and a priority, and for DQ, it'll return the smallest priority value, right? And so when we NQ, we first glue them together, and then turn around and then deal with them as a glued together object. And so our tree, right, can be either empty or not empty. And so we're going to use the same objects or the same class to represent both kinds of trees. So this is slightly different than the approach we took in the assignment, where we had different classes, one for empty trees, one for non-empty trees. And that had some implications. That meant that when we inserted and removed, we might have to change what kind of tree we were. And so in your assignment, you have to recapture the results of inserting or removing. The result of inserting is a whole new tree. And so you have to take that result and replace yourself, right? So if you're inserting into your left, you ask the left to insert, and then whatever tree is the result is what gets returned, and then you reset your left to be that result. If that tree was able to mutate itself, it didn't need to change types, then you'll get back the same tree. But if it does need to change types, you'll get back a different object. And so that's why our assignment is structured the way it's structured. For the binary min tree implementation we started in class on Tuesday, we took a different approach. And I did this specifically so you can see kind of the two different ways of thinking about this, and the two different ways. And now one is not necessarily better than the other. It's just you just have to know what's going on, right? So the way we did it in class was we're only going to have one class to represent all kinds of binary min trees. And, and there was a special, we have some way of knowing that a particular binary min tree is empty versus not empty. And the way we did it, and we'll look at the code in a second, is to specifically model an empty tree using a flag inside our binary min tree structure that said, am I empty or not? And if I'm empty, then all my other fields don't have any meaning except for the ones that are well defined for empty trees. And if I'm not empty, then all my other fields mean what they're supposed to mean, right? And so that's a different approach. When we do it this way, we know that we can always mutate an object by inserting something or removing something. We don't have to ever change the kind of object it is. And so we can allow NQing and DQing into a binary min tree the way we've written it this time to be void methods, because we know that they're going to change the object we're working with appropriately. OK. And so, so the actual NQing algorithm looked like this. We glue our priority and value together. If we are an empty tree and we're trying to insert this item into an empty tree, great. That's easy. And then we just become a leaf, right? We put the item we're inserting at the roots, and we change our structure so that instead of being an empty tree, we're a non-empty tree. And we have a single value, and where size is 1. And that's kind of like a base case, if you will. And if we're not empty, then we check. We look, the thing that we're trying to enqueue, is it smaller than the thing that's already at my roots? If it is, then, OK, just take the thing I'm trying to enqueue, make that my root, take what was used to be my root, and put it into one of my children. Basically, we're saying if what we're trying to put into the tree is the smallest thing, then it belongs at the top. And then whatever was at the top, push down below, right? That's the idea. And of course, if what we're trying to enqueue isn't smaller than what's at the top, then take that and push it down below. And then to keep our invariant with our left child and our right child being trees of relatively even height, not being more than one off, we decide which child we're going to go to by looking at them and putting it into the lower height child, right? So, right. OK, so that's so just to review the code that we ended with last time, we were at, I believe, was it take 3 or take 2? Let me think here. Yeah, we're at take 3, binary min tree, right? And here was are in Q, right? So we have NQ and DQ. This is the actual interface that we're implementing, right? We did this generically in terms of value type V and priority type P. And so we are implementing a priority queue of value type V and priority type P. P, of course, has to be comparable because we need to be able to compare priorities. And the priority queue itself, right, basically just has a few operations, NQ, DQ, retrieve the minimum without dequeuing it, and your size. And our binary min tree implementation, right, wants to work in prioritized values, not just values, because we need to glue them together. And so we can see that our binary min tree is actually works with a prioritized value, right? And the way we kind of created that veneer is our implementation of the priority queue for NQ just glued together our prioritized value, and then turned around and called an NQ prioritize, which is some private method of our binary min tree class that deals with the prioritized value. And then DQ basically calls DQ prioritize, which is our prioritized version of DQ, in order to get back our glued together object. And then we unglue it to get the value back out to return it. And then get min, same deal, right? And then size, we're modeling size specifically as an integer that we're going to keep track of. We're also going to model height specifically in order to allow, so that we can, because we often need to compare our left height and our right height, so our trees should know how tall they are as well, right? Okay, when we create a new binary min tree that's empty, the way we model emptiness is we have our isEmpty flag that tells me I'm empty. And then if we're empty, then we'll set these, the root value, left, and height don't make any sense for empty trees, so they can be null. They can be, it's always good to clean it up and make them null. But the fact that isEmpty is true, that's what tells us we're empty. And then height is -1. That's well defined for an empty tree. And that was our little trick of being able to have empty trees be -1 so that leaves have a height of 0. And of course, a size of an empty tree is well defined. And so that's set to 0. And then when we create, if we create or want to create a non-empty version, given a particular value, a prioritized value, then that's our root value is our root value, and then we create new empty trees for our left and our right. IsEmpty is false, so that we don't, we're not empty, and our height is 0 because we're a leaf with 2 empty children, and our size is 1. So those are our 2 base constructors: make an empty version, make a non-empty version with just 1 thing in it. Okay, given that, we can NQ values, right? And NQ values just glues those things together, and then NQs uses this NQ prioritized. And here's that algorithm we just went over, right? If we are empty, then become non-empty. How do we become non-empty? Well, now we do have a root value, so set it to that value. Set up our left and our right to be valid, empty trees, right? Create new empty trees for them to be empty trees. And then set our flag that we're empty to be false, right? So that we don't think that we're empty anymore. And and we know that if we went from being an empty tree to being a non-empty tree as a leaf, that our height is by definition 0, right? So that's NQing into an empty tree. If we want to NQ into a tree that's not empty, then here is we need to compare the value we're trying to NQ, that's what comes in, right? We retrieve the priority from that value. Remember, these values are prioritized values, so they're glued together with the priority. So we retrieve that priority. We know that priority type is comparable, and so we compare it to the priority from the root value. And if that's less than 0, we know that what we're trying to put into the tree is actually smaller than what's at root, and it actually belongs here. So we swap them, right? So that's what these 3 lines of code does, right? It says, put this new value in the root and take the root and make it, and set it to the value I'm trying to enqueue, right? So that afterwards, after these lines of code, we know that whatever is pointed to by value, the name value, is the smaller of the two, the value we were trying to encode, enqueue, or the root value, the original root value. Whichever one was smaller, value ends up pointing to that after that swap. And if value was already bigger than the root val, then we won't swap, and value will still be the bigger of the two, right? And root value will be the smaller of the two. And now we can take the bigger of the two and put it into our children. For that, we just need to know which one's shorter. And so we have a preference for left. Doesn't really matter. But we ask the left child if you're shorter than or equal to the height of the right child. And if it is, we put it in the left. And if it's not, we put it into the right. And then the last thing, if we're putting into a non-empty tree, we have to recalculate our height. Because by inserting something into our left or into our right, whichever one we ended up inserting into, it might have changed the height of that tree, which might have changed the height of us. And so we ask our left and our right what your heights are after all this is done, and figure out which one's bigger, add 1. That's our new height. And whether or not whether we insert it into an empty tree or into a non-empty tree, our size goes up by 1, right? So an empty tree would have started off with the size of 0, and when it hits this, it'll be size 1. A non-empty tree would have started off with whatever its size was, and after it's done, it'll go up by 1. So either way. All right, so that's where we ended up, right? So that's where we ended up on Tuesday. Let's now look at the work we need to do to take something out of a binary mid tree, right? So that's how we put things in. And we know no matter how we put things in, we will always end up with the smallest thing at the top and 2 balanced children, right? And that's great. And so now when we want to retrieve something, right? So a priority queue, when you dequeue out of the priority queue, you get the smallest thing. We know where that is. That was the whole point of this, was to put the smallest thing in a very convenient place. It's at the top. And so it's always at the root. So we know that we're going to take the root of our tree, right? That's that value there. That's what we're going to return from dequeuing. But we can't have a hole in our root value. We need something to be the root value of our tree. And if we're about to take the root value that we already had and take it out and return it as the result of dequeuing from this binary min tree, then we need to replace it with something, right? And so the way we can replace it with something is we need to do that in a way that after we replace it, our invariants still hold. And that's really the power of the invariance, is to essentially guide your implementation. You know that, look, it's true before, so I can count on it being true, and I can make that assumption with my logic for how I'm dealing with my tree. And I know that at the end of the day, it needs to be true, and when I'm done. So whatever I do, I need to make sure that at the end of the day, I return the tree to a state where those invariants are true. So right. OK. So remember what those invariants are. Those invariants are that the smallest things on top and our left and our right trees are balanced with a height difference of at most 1, right? OK, so there's, if we take something out of a binary min tree, we have 3 possibilities, right? The first possibility is that the root is the only value in the tree. In other words, this tree only had one thing in it. It was size equals 1, and its 2 children tree were empty anyway, and we're just taking out the only thing that was in the tree, right? So that's one possible case, right? The other possible case is we're taking out something from the tree. We're taking out what is at the root, but we only have one valid child. In other words, one of our children is not empty, and one of our children is empty, right? That's a second possible case. And then the third possible case is we're taking the thing out of the root, and both of our children are not empty. They're both fully, they're both trees with more than at least one thing in them, right? So case one is relatively straightforward, right? If we take the only thing out of a tree, what are we left with? An empty tree, that's right, right? So for case one, right, if the tree only has one value, then then great, we have the value we're going to return, and the only thing we have to do is turn ourselves into an empty tree, right? Change our fields, right? Set that isEmpty flag to be true. Make all the fields that don't make sense equal to null. Make sure that our height is -1, because that's by definition the height of an empty tree. Make sure our size is set to 0, because that's by definition what the size of an empty tree is. So just turn ourselves into an empty tree, and we're done, right? Now, afterwards, and then return the value that we took out, right? And we know that our invariants are true for an empty tree by definition. The smallest value is on top of an empty tree. There is no value. So smallest or not, it doesn't really, yes, it's true. The smallest value is on top. There's just no value at all, right? Our left and our right trees are balanced. Sure, we don't even have left trees or right trees, right? They're both empty trees. we don't even have left trees or right trees. We're an empty tree. So that doesn't even make sense, right? There is no left tree. There is no right tree. So our invariants, by definition, are in fact already satisfied, right? Okay. Well, what about case number 2, right? If in case number 2, either our left tree or our right tree is empty, right? But it can't be both, right? And the reason why is because if it was both, that would be case number 1, right? That we've already taken care of that case, right? So case number 1, there's only one thing in the tree. Both children are empty. Case number 2 is one of our children are empty, one of them isn't, right? So, so we have to replace the thing that we're taking, which is the root value, with something from one of our children. There's only one child we can take something from, because one's empty. And so we simply dequeue, we simply take, we recurse, we ask the one a non-empty child that we have, please give us your minimum value, dequeue your minimum value, because I need to take it and install it here instead. Okay? So we'll just ask our, the one child that's not empty, we'll just recursively dequeue the minimum item from that child and put it here, right? We know that before we took out this root value, before we did this operation, that our invariance held before this, right? And we also know, because we're in case number 2, that one of our children was empty. It turns out that not only do we know that if one of our children are empty, we also know that the other child at most has one thing in it, right? It can't have more than one thing in it. It has to be a leaf. And the reason why is because if it had more than one thing in it, then it would have to have a root value and then at least one non-empty child of its own, which would make the height of that tree 1, and the height of the sibling would be -1, and the difference would be 2. And we know that our left child and our right child, the difference can only be as much as 1. So if one of our trees is empty, one of our subtrees, one of our children is empty, then at most the other child can only be a leaf. It just has, there's no other possibility, right? So, but we don't even have to worry about that, because we can ask that one non-empty child to dequeue. It'll just turn itself into an empty child. And so we know that the invariants hold in this case as well, because after this operation, the non-empty child that we started with will now become an empty child. And we know this. We know this for a fact. We don't have to check it. We can if we want, but we know it has to be the case, right? And then the other child was already empty, which means that we, having stolen the minimum value from our one non-empty child, now have turned ourselves into a leaf with 2 empty children and 1 value here. right? So case 2 is, we know that the invariants were held before the operation. We can analyze our case with respect to those invariants to infer something that has to be true, that non-empty child can only have one thing in it anyway, right? And then we know that after the operation, all our invariants will be true again, and so we're good. The last case is where the most general case, where we're not at an edge case, right? We're not a leaf. We're not near the bottom with just one non-empty child. We're somewhere in the middle of the tree with 2 children that are both non-empty, right? So in that case, again, we know we're losing the element at the root. That's the one we're going to return, right? So we need to replace it with an element from a value from one of our children. We just look. We ask our left child, what is your minimum value? Without actually taking it out. We'll just peek into it, right? We'll ask it to, because remember, that's one of our operations. We can ask for the minimum without actually taking it out of the priority queue. So we ask our left child, what is your minimum? And we ask the right child, what is your minimum? Without actually doing the DQ operation. And we look at the 2 and we say, oh, which one's smaller? Whichever one's smaller, that's the one we'll steal, right? Because we'll guarantee that that will help us restore the invariant. If I take the smaller of the 2 from my children, then I know it has to be the smallest of everything in both children, right? Because it was the smallest in the child that I took it from. That happens to be smaller than the smallest item in the other child, which means that there's no other item in the other child that could be smaller. So that's my smallest out of both my children, and that's the one I'll steal. So I install that smaller value here, and I'll wherever I got it from, I'll DQ it from that recursively from that child. Right? Now, once we do that, that's great. That helps us restore the invariant about the smallest always has to be at the root. But now we are not quite sure about the heights of our children. If you think about it, before we started, they could have been off by at most 1. And depending on which child we took the value from, it could have been that our left child was one larger, one taller than our right child, and then we took an item from our right child, and that made that tree even shorter, right? Like that it happened to make the height of that tree go even smaller, and so now the 2 children are more than 1 apart. That's a possibility. So after we've restored the minimum item at our root, we need to check our children heights. And as long as they're out of balance, we need to move stuff from the taller one to the shorter one, right? Until they're back in balance. It turns out, right, we're going to write the code not assuming this statement that I'm about to make. But it turns out you can prove that at most you only have to steal one thing from the taller child and put it into the shorter child, right? They could be out of balance, but that you should be able to restore that balance just by moving one item from the thing that is too tall to the thing that is too short. We're going to write the code not necessarily assuming that. We're just going to sit there in a while loop and make sure that, well, as long as the taller one is too tall and the difference between the taller one and the shorter one is larger than 1, I'm going to keep moving items. Turns out you'll only ever do it once. All right. OK, so let's look at that code, right? OK, so that was NQ prioritized. DQ was, again, same thing. The actual interface for the priority queue interface says you can DQ and you get back the value and the priority is thrown away. Internally, we have our own internal DQ prioritize, right, where you're going to deal with it prioritized values. So we'll dequeue the prioritized value, and then we'll strip away the priority by retrieving just the value to return. So that's the top-level interface, and then it kind of, basically is just a thin veneer for this internal enqueue prioritized, dequeue prioritized. So let's look at what dequeue prioritized looks like. And here's dequeue prioritized, which will give me back a prioritized value, and and we can see our cases. The first one is just an error. You can't dequeue something from an empty queue. And so if we are empty, and how do we know we're empty? We check our isEmpty flag, right? So if we're empty, then we need to throw new unsupported operation exception, right? That's just a wrong thing, right? We know that this root value, that's the result. That's the thing that is the thing we're dequeuing, right? If we're dequeuing from this tree, we know we're dequeuing the top thing. That's the thing we're trying to dequeue. So our result is going to be our root value, okay? And now the rest of this code is replacing the root value with something appropriate. If we're a leaf, also easy to detect. If our size is 1, right? Then we know that, we're about to give away the only thing in this tree, and so we should now become an empty tree. Well, that's pretty easy. We flip our isEmpty flag to be true. We set these root value left and right to be null because they don't have any meaning for an empty tree, just to be safe. The height of an empty tree we know is -1 in order so that it makes sense, like everyone can calculate their height from their children if they want. And our size is 0, right? So actually, I need to add that. And our size is now 0. And then we can return, right? So now we're done, and we've turned ourselves into an empty tree, and we can return ourselves. We can return the result, right? So that's case 1, right? The next two, if we're not in case 1, the next two else ifs are the two versions of case 2, that our left is empty or our right is empty. We know that both won't be the true because that would have been case 1 right here, right? So we first check if our left is empty, well, then the root value that needs to be here is our right, right? So tell our right, please, you dequeue your, dequeue prioritized. We don't have to go through the dequeue, right? We want the value with its priority, so we ask the right to dequeue prioritized, and we'll get back, right? The right will go ahead and adjust itself and do whatever it's going to do recursively. So we know that at the end of the day, right will have changed itself to be appropriate for having taken out the minimum thing, and now we have it. And we can set it equal to our root value here. And then the opposite is, oh, no, right is empty. OK, so dequeue from the left and set it here, right? If we're, and then the final case, this is case 3, they're both not, they're both not empty. Then I'm going to get prioritized min, just like in our prioritized queue interface, we have a get min that retrieves the min without dequeuing it. Then in our binary min tree, we have a prioritized version of that that'll work with a prioritized value. So I ask for the prioritized value, the minimum from left, and I ask for that same thing, the prioritized value minimum from right. And that doesn't mean I took them out. It just means I retrieved them, right? So the left and right didn't change themselves. I haven't operated on left and right yet. And now I can, extract the priority from what I received from my left and compare it, because the priorities are comparable, to the priority from the right. And if that's less than 0, I know that whatever I got from my left child, that one is the smaller of the two. And so I can ask my left child, please dequeue your minimum, right? I already know what it is, right? I could have used it here, but when I ask it to dequeue, it's going to give it back to me again because that's the result of the dequeue operation. So I ask the left to dequeue its prioritized value, and I install it as the root. If it was the other way around, I steal it from right. And so now I know I've set up my invariant for where the minimum is correctly. And now I'm going to balance my trees. If my left height and my right height, now that I've taken the appropriate, I've stolen the appropriate value from one of my children and installed it here, if my left tree's height is not equal to my right tree's height, if they're equal, I'm done, right? They're already in balance. But if they're not equal to each other, then I need to know which one's taller, right? And so I declare a local variable taller, and I set it either to left or right, depending on which one's taller. So if left is taller, right, get height of left is strictly larger than right, then my taller needs to be set to left. Otherwise, it needs to be set to right. So this is all one line of code, right? This is all one statement. And it's using that ternary operator where we ask a question, a Boolean question. In this case, is the left get height strictly greater than the right get height? And so we're asking that question. That's this question mark. And then if yes, then we get the first thing, which is left. And if not, then we get the thing after the colon, which is right. And so one of these two is going to be the result. And I'm going to have taller equal, like my taller name is now going to be a reference to either left or right, depending on which one's taller. I do the exact same thing, but now asking for which one is strictly shorter, and again, setting the name shorter to be equal to either left or right. I know that taller and shorter will point to different things. Like one will point to left and one will point to right, because one is strictly taller or shorter than the other. They can't be the same height, because if they were the same height, I wouldn't even be inside this if statement. The outer if statement said if we're the same height, then we're done, right? Like then we're already balanced. So so if we're inside this if statement, then they can't possibly be the same height, and therefore one of them has to be strictly shorter or strictly taller. And so now we know which one's which, and we have a reference. The taller one is pointed to by taller. The shorter one is pointed to by shorter. And now we can basically say, well, I know the taller one is going to be larger than the shorter one. And as long as the taller one minus the shorter one, their heights, as long as that's more than one, right, as long as they're more than one apart, right, because they can be either equal or one apart, but they can't be more than one apart. So as long as there's more than one apart, I'm going to take an item from my taller. I'm going to ask the taller to dequeue an item, and I'll enqueue it in my shorter. So basically, this line of code here, line 126, is just shuffling from the taller queue to the shorter queue, taller child to the shorter child, until taller and shorter either are one apart or zero apart, right? OK. So whether or not I had case 2 or case 3, at the end of the day, I need to make sure that I update my information. So the case 1, we knew all the values here, right? Like case 1, when we became empty, we knew height was now -1 and size is 0, and we returned the result and we were done. Everything here, right, where we possibly stole from our left or possibly stole from our right or possibly, shuffled things from one side to the other, we need to make sure that our information about ourselves is updated, right? So we recalculate our height as the maximum of either our left hand or right hand side plus 1, right? And we know that we've taken one thing out of our queue, right? The thing that we're about to return, the result, that was our old root val, right? That was the thing that we replaced. That was the thing that we set to result way at the beginning, and then we replaced root val appropriately. So we know we're going to lose 1, and so we can just subtract 1 from our size, and now we can return our result. Okay, and that is the code for dequeuing. Okay? All right, so let's pause there before we move any further, and if there's any questions about what we've seen, because that's pretty much how the binary min tree works. And now we have a binary min tree that implements a priority queue. Yeah.
So would that mean that, like, with the priority queue, and it would be like the most minimum, and it's like the second?
Yeah, that's right. So the minimum thing is always at the top. We know that, right? So where's the second smallest thing? Well, it's got to be one of either the left or the right, right? But now the third smallest thing, that could be, it doesn't have to be the other one, right? It could be, further down on the underneath the second smallest thing, right? So it's not that we know exactly where the ith smallest thing is, right? But we do know that the general, like the relationship between the top and anything below it, right?
So we're talking about binary min trees right now. Is there a difference between binary heap or like?
Yeah, we're going to get to a binary heap. A binary heap is basically a better way of doing this, right? Where we do it all in a list, right? And that's what we're working at, right? We're working toward, yeah. So, and that's why I caveated way back on Tuesday as well as at the beginning of today. No one actually uses a binary min tree, right? So, but the nice thing is it kind of is it's a nice analog to the thing you're doing in your assignment, right? But and we could do a priority queue as a binary min tree, but we have an even better way of doing it, which is that binary heap, right?
And so for the priority queue, when you're like doing that together, that like the number, like the priority number, is like basically telling you which one is the weakest.
Yeah, so when we enqueue something into a priority queue, we have to provide a value and a priority. We've generalized our implementation so that we don't care about the types of either the value or the priority. We just need the priority type to be something that is comparable. So we have that at the very top here, right? A binary min tree is defined in terms of a value type and a priority type, where that priority type has to be comparable. That's how we are able to compare things, right? And that's. But then, when we are given a value and a priority to enqueue, because those things need to go together always, we basically glue them together into what we call a prioritized value, right? So that those two things are together, and then we operate on that prioritized value, right? So we have an enqueue which matches the interface that we're trying to provide, which is you give me a value and a priority. And we have a dequeue that matches the interface we're trying to provide, which is I'll give you back the value. But internally, we have matching versions of those that work in prioritized values. And when all we do is we glue them together and then turn around and work with the internal methods that we have that will work with them glued together. Right. Okay. So let's try it out, right? Like we haven't actually tested this code. We haven't actually seen if it works. So let's actually see it in action. So here's a little main program where I have a priority queue of strings and integers, right? So strings are the value type. Integer is the priority type. It's comparable, right? And so that's good. And I need it to be a priority queue. What I want is a priority queue. So what I want is an object that will provide me with the interface of, right, enqueuing a string with an integer, dequeuing strings from the priority queue, being able to ask which string happens to be the minimum without dequeuing it, and asking for the size of the priority queue. So that is the interface I'm going to use it for, right? Use it with. The actual implementation, right? So that's what I need, right? What I need to create, right? So if that's what I need, then that means I need to create a actual real structure, a concrete implementation of this interface that will give me that interface. That's our binary min tree, right? So our binary min tree, which operates on string values with integer priorities, is my priority queue, right? So I create my new binary min tree. That is my priority queue. It provides that interface, and so now I can use it. So I can enqueue apple, banana, carrot, and date with the priorities 3, -4, 132. I just made these things up, right? And then and I know what I should expect back out. I should expect them back out in order of of increasing priority. So the first thing I should expect back out is banana, because that's -4. That's the smallest of the 4 priorities I inserted. The next thing I should expect out is apple, and then date, and then caret. And so if I sit here and just call DQ 4 times in a row and print out the results, right? DQ is going to return the string, which is the removed highest priority string, right? And so the priority queue will go from size 4 to 3 to 2, to 1 to 0, right? And I print all these things out. I will hopefully, in fact, I get back exactly what I expect, right? Banana, apple, date, caret. All right. So this is a probably, so again, I know that I keep promising we're going to get to binary heaps, and we will, but I really want to kind of, because you guys are doing something very similar with binary search trees, it allows me to use this binary min tree to kind of really show you what's going on in the machine when you're working with these kinds of tree structures, right? And it's a good context for revisiting the idea of recursion and base cases and exactly what's happening in the machine. So what I'd like to do now is actually essentially trace through what happens when we do this little main program, right? OK. So because I'm going to be flipping back and forth between code and the slides, I'm not going to go into presentation mode, and I'm going to we'll just do it this way, right? All right. OK, so we'll start off at line 6 of the main program, OK? So the way I'm going to show this is I'm going to show our stack and our heap. This is the model of our machine, right? When I have a line number at the top, unless it says pre in front of it, it basically means we're at that line and we've just completed that line, right? We've just, so the main program, line 6, if we look at what that is, that means here, right? So essentially, I've declared PQ, and I've set it equal to a new empty binary min tree. What does our machine look like after line 6? It looks like this, right? We have our stack that keeps track of our local variables, our parameters to the method. We're at the very top at main. So I'm ignoring args, right? So we have one local variable at this point, PQ, right? And it points to, it references into memory to a structure, which is our new empty binary min tree, right? And what that looks like, right? So if we look at the code for our binary min tree, our binary min tree has fields, right? That's the data, right? That's the stuff that make up a binary min tree. And if we kind of look at what it looks like in memory, right? This is an empty binary min tree, so isEmpty is set to true. Root value left and right have no meaning and have been set to null, so those are all null. Our height is -1 because we're an empty tree, and our size is 0. So that's the state of the world. That's our machine at, after line 6. All right, so let's see. Let's keep going. So we're here at line 6. And now we're about to enqueue apple. OK? So we're about to enqueue apple. And so we're calling the enqueue method on our priority queue, right? Our priority queue is this binary min tree. So we're about to call the enqueue method that is provided by our binary min tree as the implementation of this priority queue's enqueue operation, right? So we are essentially going to, where are we going? We're going to this spot in the code, right? Line 32, where we're about to enqueue a particular value with a particular priority, right? And so after we're here, right? What happened at line 32? Well, we took our value and our priority, and we glued them together into a new prioritized impl, right? Which is our implementation of prioritized values, right? And that was our gluing together so that we can deal with the value and the priority together. On the machine, what that looks like is, right, so when we called enqueue, we were provided a value and a priority. In our machine, those are local variables. Those are parameters in our stack. we called enqueue on a particular binary entry, right? We called it on PQ, right? And so this is an instance method, right? We whatever PQ pointed to in main, right? That empty binary entry, that's the tree that we said please enqueue, right? And so since this is an instance method, we have this notion of what the current object is, which object is doing this, right? And that's reflected in the value of the this keyword. So this is that same object that PQ was, right? Because we said PQ.enqueue apple 3, right? And so when we go to enqueue, it is the enqueue method as being executed by this particular object, okay? And in line 32 in particular, we created a new local variable called PV as the result of having glued value and priority together. So here is our prioritized value, which has a value and a priority glued together. The string is also a reference type and should be a separate object with an arrow. But there's going to be way too many arrows and way too many boxes. So strings, we're just going to write as strings. But we know that in reality, that also is its own little box somewhere in memory, and that that value is pointing to that string object, right? But I think strings are low level enough, and we kind of understand them well enough that in our diagram we'll just have them be there as they look like values, but they're really reference values, right? But now our PV, right, our local variable PV here now points to this glued together thing. Okay? So let's keep going. So now that we have this thing that's glued together, we're about to, over here, right, we have this thing that's glued together. Now we're going to call enqueue prioritized. Enqueue prioritized is being called on this, right? We don't have to say it specifically, but it's the same thing as saying this.enqueue prioritized, right? It's an instance method on the same current object, right? So that's going to take us to, we're going to take that glued together object, and we're going to send it to this enqueue prioritized method, which is going to take us down here to line 58, right, when we call enqueue prioritized. When we call enqueue prioritized, we end up in, right, our stack, right, grows, right? Now we're in a new method, right? So we have a new call frame. The this pointer for enqueue prioritized is the same one that it was for enqueue, right? Because we're still working with the same object. All right? So that's and so this is after having done lines 58 through 63 and 79. So let's go back to that. Right? So we're here at 58, right? And our this pointer points to that same object that we had up here in enqueue, which is the same object that we had here in PQ, right? That's fine. And our first thing is, are we empty, right? And we can look in ourselves and say, we can go through this, right? So, getting to isEmpty here is the same thing as getting to this.isEmpty. So we look at isEmpty, and in fact, we are, oops, that should be, oh yeah, right. Originally it was true, right? We were empty. And because we were empty, then we took our value and we set our root value to be that value. We set up a new empty tree to be our left. We set up a new empty tree to be our right. We changed our isEmpty value to be false, and we set our height to be 0, right? And that's right. And then after all of that, we increased our size by 1. And so that is now the situation, right? We set our root value to be the value that we're enqueuing, right? We set our left to now be this empty tree, this new empty tree that we created. We set our right to point to this new empty tree that we created. We set up our isEmpty to be false because we're no longer empty. We set our height to be 0. And then our old size was 0. And at the very end, we added 1 to it. And so now our size is 1. So after we execute lines 58 through 63 and then line 79, right, which is essentially all of this, right, and then this, We're about to return. We're done enqueuing our prioritized, and this is the situation we're in. Okay? So any questions about how we got here, like how the state of the machine reflects where we are in the code, at this point? Good. Okay. We're about to go back to where we came from. Where did we come from? We came from, we came from enqueue, right? That call to enqueue. And so we're about to go back to here, right? We're about to finish this call, and that is going to return us back to main, right? Where we're done with having enqueued Apple with the priority 3. Right? Okay, so we're going back to enqueue, right? So we're back to, let's see here. Right, we're going back to here, right? So now we're done, right? We're done with enqueuing prioritize. We're now back here to enqueue, right? And now we're going to go back to main. And now we're back at main, having finished that part, and now here's our state of the world. Okay, so these diagrams, I want to keep going and do this whole stack trace thing. These diagrams are going to start to get kind of messy unless we take some shortcuts. So one shortcut we're going to take is this value and priority when we glue them together. Instead of putting them in a box and having that box be somewhere in our heap and having a pointer to it, I'm going to make it look like this with a box that has the string and a little bar and then the priority. So whenever you see that kind of structure, that basically is the a prioritized value, a priority and a value glued together, right? And I'm going to sometimes put that box here in root val. It really is somewhere else in memory, and this root value is pointing to it, right? But where it's convenient, I'll actually just stick it into where root val is pointing to it, like just right there inside, as if it was inside that other object, just to kind of clean up the picture. But in reality, every box is its own box, and then any reference to it is an arrow, right? Okay. So so now we're done with Apple, and now we're about to enqueue banana, right? Well, okay, so we call enqueue for banana. I'm not going to go through every little step now. I'm going to skip a few steps, but we'll look at it in the code. So we're going to pass banana as a string in -4 to enqueue, which will first glue them together into a new object, and then turn around and call enqueue prioritized with that new glued together object. And then it'll put us here in line 58, where we're saying we're basically trying to enqueue this prioritized object, right? Well, when we get to line 58, right, our binary min tree is no longer empty, right? We're starting again with PQ, right, the very top binary min tree that we started with, and it's no longer empty. So this part doesn't apply. Instead, we end up here in line 65, right? And we are comparing the value at our that we're trying to, the priority of the value of what we're trying to insert with the priority of what's at our root val. And so our machine looks like this, right? So we enqueued banana in -4. That created this prioritized value where we glue those together. And now we're enqueuing prioritized this glued together value into that same tree, right? And now our tree, I've had to move things around so we can kind of see it as a tree, right? We can see our original PQ is now is up here with a root val of this structure with Apple and 3, and a left and a right that are these two empty values, right? And when basically at line 65 of the binary min tree, where we're saying is banana's -4 smaller than Apple's 3, right? So that's right here. This banana's -4 compared to apples, root value, right, this guy's, get priority 3. It is, right? So it is the case that -4 is smaller than 3. And so what happens is we're going to swap them, right? So we're gonna go into here and we're gonna say, okay, I'm gonna create a little temporary variable and point that to value. I'm gonna have value now point to what root value is pointing, and then I'll take root value and have it point back to temporary, and then I'll pop back out all the way to, at line 71, right? And so essentially, I'm going to flip their position. See? Like so here, root value was the structure apple 3, and my value, my local variable value was banana -4. Those, so this little set of these lines here saw that these, that banana really should be here, and now and so I'm going to swap those two around, and so I swap those two around, and I put banana there, right? And I put an apple here, right? So I just basically installed that banana -4 object into the root val and took that root val and made it the thing that I'm trying to push to my children. So here I am at line 70, right? Having completed line 70 and ready to keep going. Now I need to put that, I still need to push that thing down to my children somewhere. So I have to look at my heights of my left and my right. Well, if I look at my left height, it's -1. If I look at my right height, it's -1. So they're equal to each other. So if -1 is less than or equal to -1, that's true, then I'm going to ask my left, okay, go and queue this prioritized value, right? Now I'm working in prioritized values, and that's fine, right? That's the whole point, right? I've glued them together, and now I'm working with prioritized values. So when I recurse, I'm recursing on and queue prioritized, right? Because I'm trying to put the prioritized value, the glued together value, into my left tree. So when I call, NQ prioritized on left, and now I'm calling it on left, right? So here, right, at the very, very top, I had my pointer to that PQ, right, which was my top level priority queue, and that called NQ, which just glued the thing together and then called NQ prioritized. So then that was the first call to NQ prioritized. We decided that we're going to flip around the bananas and the apple, fine. But now I'm calling NQ prioritized not on the top, right? I'm recursing, right? I'm calling NQ prioritized on my left. That's why this pointer for the second call to NQ prioritized points to my left child, right? The first NQ prioritized points to the top child. I'm still doing that. As part of doing that, I've recursed. And now I am taking the value apple, combined with 3, and trying to NQ it into this empty list. So this recursion, right, where now I'm doing the same operation, but I'm doing it with one of my children. And now it's going to do the exact same stuff. The code's going to be the same, but we're working with a different structure, right? So now I am back here at line 58, but now with this empty tree as the thing that I'm working with, as what this points to. And we know what's going to happen, right? We're going to say, oh yeah, that's empty, and we're going to take the value that we're trying to encode and put it into that root val, and we're going to set up left and right to be new empty trees. We're going to flip this isEmpty flag to be false. We'll set up our height to be 0, and we'll set up our size to be 1, and that's exactly what's going to happen, right? And so after we do all of that, after we do all of these things to set that up, and get all the way down here to 79 and increase our size. We're about to return from this second call to NQ prioritized, which was working with that, this left-hand side of our original tree. And now we've set it up as a tree in its own right with empty children and a root value and the appropriate values for the other instance fields. And now now we're done with this call to enqueue prioritize. So we're going to go back to where we came from, right? And then now we're done there, right? So now we're back to where we came from, where we were, we had just done this part where we're being queued into our left. And so we're going to update our height. So now this over here, we're going to say, oh, well, our height is the maximum of the two negative ones, -1 + 1, so 0. So that gets set up correctly. And then we're going to increase our size. And that's going to increase our size from 0 to 1. And then now we're done there. And so now we can go back to where we came from, which is to, right? And then, oops. And then we're all the way back at main. We've finished enqueuing banana, right? And now we have our new tree here, right? All right, let's do carrot then, right? Great. So we're about to call, right? So when we, we can do carrot, and we can do, and after we do carrot, so I'm not going to go through all the steps, but after we do carrot, we'll see that when we start off, right, when we're enqueuing carrot, right, this is our situation. We're going to glue them together and eventually end up in enqueue prioritized at the top level. We're going to look at our left and look at our right. We're not empty, fine. We're going to, it's going to be that carrot does not belong here because its priority is much larger than banana. So we don't have to swap anything. We're going to look at our left and our right trees. And we're going to say, this tree has height 0. This tree has height -1. So we know we're going to put it to our right. So we'll go to here. That will then take that carrot -100 and recursively call on our right. We know what's going to happen here when we recursively insert into an empty tree. It's going to turn itself into a non-empty tree with empty leaves, with empty children, and then return, and we'll adjust height and size again, and then we'll return, and then we'll get back all the way to the top, and that's, we'll end up in this situation. So we'll do exactly the same sequence of steps for inserting apple, right, or inserting banana, except that this time we don't have to do the swap because carrot was already bigger than than the banana was. But we do recurse to the right. We know we recurse to the right instead of the left because we already had something in our left, and so its height was 0. We didn't have anything to our right, so its height was -1. And so that was the shorter of the two trees. So that's where we ended up. And so then we at the end of the day, we end up with a tree like this, right? And then if we do it again, then we will do that with date, right? Date has a priority of 32, and so as we'll see that, this is the situation we start with, and then we'll see, 32 is greater than -4, and so we know that it's not going to swap with the root, fine. So fine, we have date 32 that we're going to push to one of our children. We're going to look at the heights of our children. Our left height is 1, our 0. Our right height is 0. These are two equal height children, so we have a preference for left. So we'll push it to the left, and so we'll recurse on the left. We'll insert date 33 into this child here. We'll go through the same process. 33 is bigger than 3, so we don't have to swap, right? We don't have to change our root, but we do need to send it down to our child. We have two children, a left and a right. They both have height -1, so we'll prefer going to our left. And so then we'll recurse, and we'll go down to this empty tree, and we'll say, OK, you put this prioritized value there. And then that empty tree will turn itself into a non-empty tree with empty children, and so we'll end up like this. Now, because we have to constantly be creating these empty trees, I'm going to kind of create a little shorthand here, right? Instead of, empty trees are, just there's nothing interesting in them, so we'll just like collapse them into a box that just says empty BMT. And in fact, right, in order to be even make it so that we can be even a little less messy, I'll just use the words, the letters ET to mean essentially a reference to an empty tree. But like string, you should remember, like when you see, this version of this diagram, that ET, that empty tree, really is a structure somewhere in memory, and that left is really a pointer to that empty tree. But for the purposes of keeping our diagram relatively sane, an empty tree, we won't have a whole box or empty tree since there's nothing in it, and we know exactly what it is, and we'll just use the word, the letters ET to indicate a reference to some empty tree somewhere in the heap. Okay, so that's how we ended up with our 4 things into the tree, right? Now let's see what happens when we take them out, right? So now we get to the next line of code, and we're calling dequeue, right? So we're asking our priority queue to dequeue a value. Same kind of thing, right? So we go to the dequeue method. And the dequeue method is going to turn around and call dequeue prioritized. And the result of dequeue prioritized is what we're going to store in this local variable PV. So we don't know what PV is yet, right? We're in the middle of trying to figure it out. We're saying, OK, go dequeue. So we're now in dequeue prioritized, right? And we're in line 84 here, right? And we're working with this, the same top root level tree, and we're basically about to, dequeue an item here. Well, we're not empty. That's obvious, right? So good. Right. So then our next thing to do is, oops, right? Is OK, result equals our root value. That creates a new local variable, right, on our stack. That equals our root value. Remember that box, banana -4, that's an object in and of itself. So root val as a field points to that box. I put it there just to be convenient. But now results as a local name, as a local variable in dequeue prioritized, also points to that same box. And now we have to decide, OK, is our size 1? No, our size is not 1. Our size is 4. So none of this will apply. We're not case 1. Is our left empty? No, our left is not empty. Here's our left, right? It's not empty at all, right? And so that won't apply. Is our right empty? No, our right is not empty either, so that doesn't apply. So we must be in this case here, and so we should retrieve from our left, what's your minimum prioritized value? And then we'll ask our right, what's your minimum prioritized value? So we're creating 2 new local variables, left min and right min. The result of asking our left child what their minimum was and our right child what its minimum prioritized value was, that's what those get set to. And so I now end up with this situation, where I am right here at line 1, right after 111. The line numbers are slightly off. But where I'm right after 111, where I've set up my left min and right min names, my local variables, to be those glued together values from my left child and from my right child, because I asked my left child, please give me back a reference to your minimum prioritized value. And I did the same thing for my right child. And so it's at this point here where we can now ask, which one's smaller, and then recurse. All right, so this took a little longer than I thought. So we'll have to pick it up there after spring break. We will eventually get to binary heaps. So go ahead and go through the slide deck and go through the code and kind of see how they correspond, because understanding how this recursion actually gets done on the stack with the objects on the heap will go a long way toward understanding your code and being able to find bugs and figure out what's going wrong. Right? All right.